Welcome back. We proceed now. We're discussing RF operation, and we discussed how adjacent cavities are magnetically coupled. And here we are considering an 8-cavity magnetron structure. And the field inside these gaps is as a standing wave field. Now, we can understand the reason why this magnetron are referred to as traveling wave magnetron and try to explain. The cavities of an 8-cavity structure are shown in a linear combination, as you can see here. This is the cavity 1, capacitance, inductance, second cavity, third cavity, and all 8 cavities. It's an equivalent structure to the cavities. The electric field pattern in a standing wave with direction of electric field lines across the cavity gaps oscillate back and forth as the RF voltage on the anode segment oscillates. You can see here the fields across the gaps. Now, the standing wave in turns can be thought of as consisting of clockwise wave and anti-clockwise wave. Two waves are constructively interfering to form a standing wave. At time t, the left moving and right moving waves combine to maximize the electric field here across the gap. And this happened in every second cavity. Electric field is maximum in this cavity, then it is maximum in this cavity, and not minimum in this cavity, maximum in this cavity, and so on.
Dr. Mohammed, may I ask you another thing?
Yeah, sure.
How the electron rotation frequency is synchronized with the RF frequency?
Okay, this is done by applying magnetic field and the anode voltage for a particular magnetic field and a particular anode voltage. They are synchronized because the frequency of rotation is controlled by these two fields.
Okay, magnetic field, electric field, constant ones.
Yeah. Magnetic and electric field are constant in the operation.
They are constant in the operation.
Yeah. Now all the phenomena are taking place with the interaction of RF field produced inside the cavity, especially when they are passing near these slots in the cavity.
RF frequency is determined by the size of the cavity.
Yeah.
That's fixed.
That's fixed.
Yeah. Because of the construction it comes.
Yeah.
Yeah. But the rotational speed of the electrons, so that they should be in synchronized manner with
In synchronized, but all are not synchronized. Few are faster, few are slower.
Yeah.
Few are come back faster, slowed down. Then when a spook is formed, energy is continuously pumped by E field and is converting into the RF field.
I see.
So at that time, forces that compress the spook are maximum. So at time t1, we have discussed at t2 here. Yes, here. The phase of wave moving to the right and wave moving to the left are such that the fields on the wave are opposite and so they cancel. At time 2, the two waves, counter-propagating waves, one is clockwise, other is anti-clockwise. The phase are cancelled and there is no field in, and no force is exerted onto the spook. As the electron spook move by the gap between cavities, the electric field is zero. And at time t, the field from the two waves again add. But this time, the field is maximum at the second, fourth, sixth, and eighth gaps. Initially, the field was maximum in this gap, in this gap, this gap, and this gap. Then comes a phase when comes a stage at time t2 when these phases are cancelled, and then another stage when fields are maximum on these gaps. Again, the forces that compress the spook are maximum. Thus, it is clear that to optimize the interaction of wave on the anode with movement of spook, the velocity of wave on the anode must be near the spook velocity. Then energy exchange from the electrons to RF field is maximum. You have to consider or to see the spook equation once again, spook figure here. Here we have seen the 8 cavity magnetron. When spook is formed, every second cavity spook is present. When this spook moves ahead, there is no force inside this region. Here it is suppressed by the RF field present inside. Then it moves ahead, there is no force. It is again in this, and meanwhile the phase have been changed. Phase of the field have been changed, and spook is in this cavity maximum and interact with the field and produce.
The electrons within the cavity, are they interacting with the E field?
Not inside the cavity, but they slightly are in the opening of the re-entrant cavity.
Right.
So the presence of these electrons affect the capacitance of that cavity. And as I have already explained that perturbation defines the effective frequency.
The question comes to my mind: how the electrons come out of the cavity? They enter in the cavity and they are coming out of the cavity.
Okay. I was explaining this thing
Did I miss this?
in the previous slide. Here, the force. Here you can see the field is maximum.
Yep.
And electric field compress the electrons away from the cavity. Then there is no field in this gap at time t2. Yep. And at time t3, there is again a constructive interference. Electrons moving to the, actually now the in free space, the force acting on the electron when there is no RF force on the electrons or spook is electric field provided to the produced by voltage provided to the node, and they are again moving towards the cavity. Cavity opening here, and they are again compressed by the field RF field present inside, and again they are in gap feeling no force, and under the influence of electric field they move upward, and again they are compressed back to the anode, and the spook move from one cavity opening to other and so on. And when it is these spook interact with the cavity, electrons of the spook interact with the RF field, their energy is decreased. That's why they come back. They gain energy from the field, electric field. They go again into the spook, and that decreased energy is converted into the RF path on every time it passes through the cavity opening. We were here, perhaps. Okay. Okay. Now we talk how modes are formed inside the magnetron. To understand the formation of modes inside the cavity, consider three pendulums. These are one-dimensional pendulum. They can move only one dimension along the line of this line. They can move this way, this way, this way, this way, this way, this way. Now there are many modes depending upon their motion. All can move in same direction, come back. They are synchronous. This is zero mode because there is no phase difference between these one. Then if you talk about two are moving in such a way that one is moving in 180 out of phase. This one is called pi mode, and so on. There can be many modes, 2 pi by 3 modes, and so on. Similarly, in the cavities, pi mode is the most favorable or efficient mode in which the RF is produced. And in this mode, RF field in here will be in this direction, and the next cavity it will be 180 out of phase. But when electrons passes from in front of this cavity here, they see the field in opposite direction, which slow them. They come down, give their energy to the RF field, amplify the RF field. When they move to the next point, the polarity have been changed. Now they again see the field in opposite direction, and their energy is decreased, and the energy have gained during this process due to potential applied to the anode. Kinetic energy they have gained is again converted back into RF energy. RF is continuously amplifying whenever they pass through this slot. So now the modes are very important because you want to operate your device in pi mode. Other modes are exist. And second problem is that if you increase the number of these cavities, your efficiency is increased. But number of modes also increases. These modes are distributed in the same frequency range. And when these modes are increases, the mode spacing between them decreases, and your device can jump from one mode to another mode, and again jumping back and forth among the mode, and RF produced can constructively, destructively interfere, and efficiency is affected, and frequency is also changing because every mode has a different frequency.
The 8 cavities is optimal?
No.
No.
Well, we shall discuss in detail how these things are optimized in coming slides. Actually, number of modes is defined by number of cavities. In accelerating structure or linear structure, number of modes are equal to the number of cavities. But here, it's a closed loop. Number of modes is divided by number of cavities divided by 2. Here are 8 cavities, then number of modes existing in this structure are 4, and by 2 there is number of modes. So these modes occur because of there are many resonators. Every additional resonator contribute to an additional mode. The mode are designated by mode numbers, which is the number of times the RF field pattern is repeated in going around the anode once. How many times the RF pattern is repeated when electrons revolve or RF revolve, because electrons and RF are now synchronous, revolve around the complete one cycle around the cavity. So if phi mu represents the relative phase change of AC electric field across adjacent cavities, then it is defined as 2 pi n by n. N capital is number of cells, and here n can be 0, plus, minus 1, 2 into n by 2 minus 1 if we have a odd number of cavities, and it is n plus minus n by 2 for even cavities, which means that there are n by 2 modes exist in the cavity, can exist in the cavity. If we want pi mode to excite, which is the most efficient mode to produce RF, what we have to do? Let's discuss first what is meant by zero mode. Zero mode means when you see the field profile of a cavity. In every cavity, alternating RF field is in same direction. There is zero phase difference between these modes. And one electron or spool passes one cavity to another cavity. In meanwhile, the phase inversion takes place. Now all phase in all cavities are in the same phase. There is zero difference, but polarity have been changed. Now field will be opposite, which will decrease the energy of the electrons, and the next one it will increase, decrease, and the net gain in this zero phase will be zero, and no RF will be produced. RF is produced, it is absorbed, produced, and absorbed. So it is not a favorable mode. Only most favorable mode is pi mode.
Dr. Mohammed, if the number of cavities are odd number, what happens?
I have explained. Then you can define the n by this one.
Even ones, isn't it?
Yeah. If even one, this term will be last term. If it is odd, this will be last term. The number of even or doesn't matter, because if your phase is pi mode, in pi mode, and it continuously changing, the change will follow the synchronous motion of electrons with the RF field, and in every cavity, in front of cavity, whenever these electron passes, they amplify the RF field. Now, what is the effect of other modes? We can discuss here. There is an infinite number of electron velocities that can excite any given mode. Initially, when we start the magnetron, there is random velocities of these electrons. They produce every type of frequency, a range of frequency, and we have almost all modes are excited, but only those modes which are resonant to these cavities have survived. More than one mode can survive, and how to mitigate them we shall discuss in the coming slides. The electric field distribution along the anodes for pi mode is shown for various time intervals. Here time t, 1/2 time period, 1 period, 1.5 time period, and so on. Here you can see the field is maximum. The next half time it is minimum, maximum, minimum, maximum, minimum. Those electrons which are synchronous with the electric field will follow this path and will gain, will contribute every time to the RF power and will amplify. But there is another situation can arise, this one. Few electrons can be such that they are slow, they passes, when this one, there is no field in this one, they passes very slowly at that time when there is field in this one, and they also contribute. This is the third mode. And so for the higher modes are also contributed. So these contribution of RF to the higher modes is a problem because they have different frequency, and we want to eliminate that situation where higher modes are contributing to the field.
I'm sorry. This is one.
It is the same one. This one?
Next to set last one.
Okay.
The current angle.
Last one?
Yes.
This one?
Electron represent one.
Yeah, yeah. Line one means when they pass this one, this is the line one, electron passes through this, it is contributing. Field is in the favor to contribute the RF. When they are here, field is maximum inside the cavity. When they are here, field is maximum inside the cavity. So this line represents the desired mode you want to excite in the magnetron. Please?
The pi mode is the most efficient.
Yeah, pi mode is most efficient. But there is possibility that other modes can be excited by these slow moving, few of them singly. So now electron represented by line 3 travel at 1/3 of the velocity of electron represented by line 1. And they have 3 pi mode. Their transit angle is 3 pi, not 3 pi mode. There is no 3 pi mode in the magnetron. A complete cycle of oscillation of RF circuit occurs while these electrons pass by each anode segment and traveling from one cavity to next. Still, these electrons are synchronous with RF field and give up energy on every third cycle of RF field. This situation is analogous to keeping the pendulum shown previously, as I've shown the example that somehow you are moving your pendulums in phase, and one of the pendulum is continuously tapped, and you are increasing or decreasing its frequency, and that frequency change cause the will push you away from the synchronous condition. One of the pendulum which is being disturbed or perturbed by external force will have different resonant frequency. Now, close to the resonator gap, the electric field is square wave. And this field is broken into the harmonics component, or number 1, 3, 4, 5. And these harmonics, and it is found that the electron represented by line 3 are in synchronous with the third harmonic. This one is line 3. So this line representing the third harmonic of this field, mode 1, we are considering the pi mode. Similarly, electron representing the lines 5, 7, and infinite set can also represent the other higher order mode of pi mode. In principle, any of these harmonics interaction can produce oscillation in the pi mode. Each of other magnetron modes can be broken into an infinite set of harmonic components and can therefore in principle be driven by electron having an infinite range of velocities. The resulting possible array of magnetrons operating condition is bewildering, and this is perhaps what led Boot and Randall in their 1975 article. They written that if this condition was considered, if this point has been appreciated in 1939, it was doubtful that the magnetron would ever have been made. Now, the radius and angular velocities of the space charge cloud which is surrounding the cathode increases with the applied anode voltage. And we know that there is a full cutoff parabola we can't exceed, except for we have already discussed the negative frequency magnetron in which anode voltage is greater than the full cutoff condition. When the angular frequency is such that the cloud is rotating in near synchronous with one of the RF mode, or one of the harmonics component of RF mode, noise current on that space charge cloud may cause oscillation to start in that mode. So not only pi mode, but harmonics of that pi mode can also be excited. The voltage at which the oscillations are initiated in various modes and various harmonics are the Hartree threshold voltage. So there is a lower limit as well. Below that limit, this oscillation cannot be started and no RF will produce. That low limit is called Hartree voltage. Here the dashed lines represent harmonics of N3 mode, which has a threshold voltage nearly identical to the N4 mode, which is the pi mode. The mode distribution is such that if you have 4 modes, the central mode will be pi mode. If you have more cavities, suppose you have 18 cavity and the 9 modes are there, the 5th mode will be pi mode. The central mode is pi mode. The first mode is the lowest frequency 0 mode. So there are a few techniques used to separate these modes because increasing the number of cavities decreases the mode separation between these frequencies or modes, which can cause problem. So the frequencies of various modes are very close together. The separation between N3 and N4 mode is only 1 to 2% for structures having more than 8 cavities. And if we have more than 8 cavities, then separation in frequency between pi mode and its nearest neighboring mode become even smaller than 1% or 2% of the frequency. Because of frequency instabilities, when the mode separation is small, your operation of the magnetron can jump from one mode to the other mode. And definitely the frequency will change. There are 3 techniques which are used to increase the mode separation between these modes. One is called strapping. The other is called rising sun structure. The structures are modified. And the third one is called coaxial. You totally modified the structure of the magnetron, and that is called coaxial magnetrons. We shall discuss in detail in the all these three techniques. In the desired pi mode of operation, alternate mode separations are at the RF potential. So if alternate segments are connected together by wires, if you have 8 cavities and every alternate cavity you short with a strap. First cavity, third cavity, fifth cavity, and seventh cavity are short. Then this technique is called strapping. What is the effect of this strapping? The straps add capacitance to the circuit. So the pi mode frequency will be altered. This is no problem when you're designing your magnetron. You can add this capacitance in your design and finalize the capacitance in such a way that by adding these straps, your capacitance is the desired capacitance. Considering the capacitance perturbed by the spook passing near the cavity, the perturbation also change the capacitance. So in modes other than pi, the voltage difference between alternate anode segment is not zero. So the strap introduce inductance as well as capacitance, resulting in different frequency shift than other for pi mode. The effect of strapping on mode separation in 18 cavity is shown here. You can see fourth mode is pi mode. No, this time fourth mode is not pi mode. It is 18th cavity. There are 9 modes. The central mode will be the pi mode. Actually, fifth mode will be the pi mode. This red line is unstrapped mode separation. 1, 2, 3, 4. This one is the pi mode. The frequency of the fifth mode. Here the wavelength is shown. When there is no strapping, this one is the fifth mode. This one is the third, and this one is the fourth. If you draw a line from these three parallel to this axis, you will see that there is a very minor difference between the wavelengths of these three modes. Modes are very close to each other. But after strapping, your fifth mode is lying here. And if you draw a perpendicular line, you will see the mode separation have been increased. So you can increase the mode separation to avoid more jumping by add straps to every alternate cavity. The next one is the second technique which can use to separate these modes, can be used to increase the mode separation is rising sun technique. You design the cavity in such a way that one cell is larger, one is shorter, larger, shorter, larger, shorter, and so on. 9 cells are, again, we are considering, I think it's 18 cavity structure.
Resonance frequencies are different. Two different resonance. Isn't it?
We are going to discuss it. The resonant frequency is collectively will be described here. Higher frequencies will be defined by shorter cavities, and low frequencies will be defined by this larger cavities. And you go back to this. Here we have 1, 2, 3, 4. The fifth mode is lying somewhere here in these dash lines. It's not shown here, but it depends how efficiently you design your star like magnetron structure. If you are very efficient and your fifth mode is lying here, then there is a huge mode separation between mode 3 and mode 5, and you have achieved your desired results. Now, the number of modes in the rising sun magnetron is the same as the strapped magnetron. In the rising sun magnetron, half the modes are such that the large cavities control the frequency, and so the frequency associated with these modes are relatively low, because as you increase the volume of the frequency, sorry to say, volume of the cavity, frequency decreases, and you raise the volume of the cavity, frequency decreases. So frequencies in the with lower modes are defined by smaller cavities, by large cavities. Large cavities have small frequencies. In the pi mode, the frequency is midway between the resonant frequencies of the two cavities. Does the rising sun structure increase the frequency separation between pi mode and the two adjacent modes? One is very above the pi mode, and other is very low the pi mode. By comparison in a strapped system, all the modes are resonant at frequencies below the pi mode. Now, the mode separation characterization of the characteristics of the rising sun structure has facilities that design and fabrication of millimeter wave magnetron can be achieved, because for high frequencies the problem is that your size of the magnetron is decreasing. As you go to design high frequency magnetrons, the size is decreasing, and the decreased size
of cavities is decreasing.
The whole structure.
Yeah,
cavities is decreasing, so definitely the whole structures, because you are bound to have a number of cavities. You can't increase the number of cavities beyond that number, because modes are increased, and increased mode can cause a lot of complications. So you have to 18 or 20 or 24 the maximum cavities. And if you want high frequency magnetron, design high frequency magnetron, the size will decrease. Cavity size is decreasing. That decreasing size, the side, force you to decrease the size of your anode as well. And as the size of anode is decreased, your charge density evolving inside the magnetron will be decreased, and definitely power will be less for high frequencies. But in this particular mode or one, you also can design magnetrons for higher frequencies as well.
Mentioned straps, capacitor, change the capacity.
They add the capacitance to the cavity.
How does the strap looking capacitance? Act as an electric for capacitance?
I have to go back to the slide. Here,
There's no more capacitor. But
the capacitance of the cavity is defined by this part. If you add the strap near this one, the capacitance will change. But this is a fixed change. You have a particular sized strap. You added the strap here, and it has changed the capacitance. Now,
strap over the slide.
we shall discuss in coming slides.
Hello, sir. Can you hear me?
Yeah, please.
I have a question for you. With magnetron cavity is a model using COMSOL or any other simulation program or RF model. We analyze the resonance characteristic in the slot or 3D geometric.
The resonance of cavity is defined by the capacitance and inductance. So you have to consider the whole structure to simulate in CST or any other simulating gadget you have.
CST, CST perhaps is more efficient.
Yeah, he is asking. His question is only the capacitance is considered, the whole structure is considered.
Is better than console.
Yeah, in COMSOL you have to define every bit by yourself. So
It is-
unless you know the physics, so you
It
have
has
to-
console too.
CST has very user-friendly interface.
Yes.
You can
Yeah, I
easily
see, I see.
define the structure and
That's right.
excite it. Any more question you have? Hello? Can you hear me?
Yes, I hear you. Thank you for information about you. I know it's console, but I don't know the CST.
The best one is you are much familiar with the simulation tool, which you are much familiar is best one for you.
Thank you.
So here comes another one. Coaxial magnetron. This one is the third technique to deal with the modes. This structure is surrounded by a single high Q cavity operating in TE011 mode. Previously, we have seen that the resonant cavities are in outer periphery of our anode, are a part of anode. But here you can see the cavities are inside this. And spook is moving here. And that's why this configuration or design is named as coaxial
Where is the
magnetron.
cathode? Where is the cathode? Cathode.
Out.
Cathode is.
Cathode is
It's in the center, but it's not shown here at this moment.
yeah,
No,
I think
because-
The center?
The
I don't know. Sorry.
the origin of the circle.
So this structure is surrounded by a single high Q cavity where TE010 mode is excited. Slot in the back wall of the alternate cavities of the anode resonator structure tightly couple the field in these resonators to surround the cavity, to the surrounding cavity. In the pi mode, the fields in every other cavity are in phase and they couple in the same direction into the surrounding cavity. This structure, this surrounding coaxial cavity helps to stabilize the magnetron in the desired pi mode of operation. All straps are not required. The anode resonators for the coaxial magnetron can be large and less complex than for a conventional strapped magnetron. Straps are here, but a few are strapped. Depending upon the configuration, that can be complex compared to the conventional strap magnetron, or can be less complex than that. So that was a one, and here we have another one. inverted coaxial magnetron. But here it is more simple, and more advantages are there in the fabrication and design, and to go for higher frequencies, because now the cavity is inside and your cathode is also the inside. Due to a large size, you can have a large anode. Sorry, your cathode can be large. These factors all combine in coaxial magnetron to produce relatively conservative magnetron design, having enhanced reliability compared with conventional magnetron. In the coaxial magnetrons, the multiple cavity anode structures has a series of modes like those of the conventional magnetron. In addition, there are various modes of oscillation of the coaxial cavity. Fortunately, the use of TE011 mode made possible for use of attenuators to damp unwanted modes. In the desired TE010 mode, the RF field exists in circular form within the cavity as indicated and decreases to zero at the walls of the cavity. Here you can see the electric field at the walls of the cavity is decreasing, and you can induce here the attenuator to eliminate the undesired modes. Here is a complete design of the cavity. You can see a tuning piston. When it is tuned in, frequency is increased. It is tuned down, out, frequency is decreased. Then there are coupling slot here. Inner circuit mode attenuator is added. Cathode is inside, and so on. And RF window is shown here. Electric field lines inside the cavity is shown. Current flow, as you have a TE010 mode in the walls of the cavity. So attenuators can reduce any other mode which is excited due to the mode jumping and any other reasons. Similarly, when field near the coupling slot from the resonator to coaxial cavity are examined, it is found that the end of the slot are free of TE010 mode. Thus, an attenuator within the inner cylinder near the ends of coupling slots does not couple to the TE010. When you has your attenuators near the coupling slot where TE011 mode is not present and it is not coupled, but any other mode which is excited will couple to the attenuators and that mode will be attenuated. Thus, an attenuator within the inner cylindrical cylinder near the end of the coupling slot doesn't couple. And another advantage of TE010 mode is that one of the cavity end plate can be made movable. You can make this end plate movable. The advantage of this movable end plate is that you can increase or decrease the volume of the cavity, and that change in volume will change the frequency of the cavity. So you have a tuning mechanism as well, and this tuning mechanism can easily be fabricated in this sort of cavity. We have discussed this one, but further we discuss its other advantages that when we, as we have discussed coaxial, and we have turned it inside out. It is called inverted coaxial magnetron. We have discussed this one. So in comparing to two structures designed at same frequency, it should be noted that the cathode size in the inverted configuration is perhaps much larger than the cathode inside the conventional magnetron. So the number of anode vanes and cavities can be large in this configuration. So two advantages are you can increase the number of vanes and you can increase also the size of the cathode. Size of the cathode contribute more charge, and number of cavities or number of vanes when increased increase the efficiency.
Is there a contribution of the length of the magnetron? Usually I see the magnetrons, the length of the magnetron is smaller than the radius. If you increase the length of the magnetron, will it contribute to the power generates?
I think there is a optimum length on which you can't increase. If we can talk about 2.6 megawatt E2V magnetron, it's other two size. This one and this one is little large, but this is not larger because of length. Length is the same. Radius and length almost are same. Perhaps it's slightly less than the other lengths. And the other, it's a coupling slot and high power HV, IHV lines or wires are going in there for the isolation. So actually the cylinder is capped in a rectangular box, and inside there is all these vanes. The power is increased by increasing the number of cavities.
Yes. I thought that if you increase the length of the
No,
cavities.
no. You can minorly or slightly play with the length, and that is changing of the volume, and changing of the volume means you are changing the frequency. Now, let's come back to the tuning of conventional. Sati, do we have more time?
Yes.
5 minutes.
5 more.
So magnetron tuning. There are two ways to tune a magnetron. One is capacitive tuning, another is inductive tuning. If somehow we introduce perturbation in the capacitive part of the cavity, it is called capacitive tuning. And the other way, if we produce any sort of perturbation in the inductance of the cavity, this one is called inductive tuning. So if you have 18 cavities, you have to perturb equally. Every cavity must be perturbed equally, so that the frequency of every cavity shifted equally and your desire is fulfilled. Otherwise, if you change the frequency of one cavity, it will be detuned, other will be tuned, and frequency will not change. Even your power efficiency will decrease. So the inductance of the cavity may be decreased or by inserting a metallic plunger into all portion of the cavity. Or coaxial magnetron can be tuned by changing the volume of the cavity within the movable end plates, as we have seen previously in this slide. In coaxial magnetron, this plate is moved up or down to change the frequency. But in conventional magnetrons, tuning is done by these two getters. Here, mechanism is shown, or we can move in or move out these tuners. You can see here, only two cells are shown where inductive tuning is produced. Here again, only two cells are shown where capacitive tuner is added or subtracted to change the frequency. A fine-tuning technique using a compressible ring in the walls of the coaxial cavity is also shown here. Another technique for tuning a coaxial magnetron, rotatable dielectric paddles. If you have attached dielectric paddles and they can slightly rotate in front of your cavity here, if you have a dielectric material and it can slightly be rotated this side and this side, then you can capacitively tune, or similarly if it is inserted here, you can inductively tune the cavity. Cavity tuning means changing the frequency as per desire. If you have a magnetron of 2.998 gigahertz, we have 3 gigahertz, it has always a tuner inside it, which can give you privilege to change its frequency 5 megahertz downward or 5 megahertz upward. So there is a play of 10 megawatts of frequency tuning in conventional magnetrons. Now, when we are tuning, the lowest frequency occurs when the pedals are aligned with the electric field. The highest frequency occurs when the pedals are perpendicular to the electric. I think it's over for now. And after,
Okay.
any question,
Sir,
please?
how to change in magnetron fields momentum and energy? How to change
Momentum.
and energy? Maybe coaxial.
So your magnetron is giving you RF field, and RF field is produced. You provide anode voltage and magnet field to the magnetron, electron, and you read the. Let me just. First slide. More we talk. Okay, this one. This one is a conventional magnetron. In the center, you are seeing this yellowish part is cathode. Inside this cathode, there is a heater which heats it, electrons are emitted, and this part of copper color is called anode. You provide HV, generally 40 to 48 kV HV. Now, this HV extract electrons. When this is heated, electrons are emitted. These electrons are 3 to 5 EV energy, and this is at very high potential. Electric field drive the electron towards the anode. Now, a magnetic field is applied perpendicular to this cathode. When these electrons move towards, they are bent due to this magnetic field effect. Lorentz force acts on it. Now, these electrons revolve around your cathode. When there are cavities and they have a resonant frequency and these electron passes in front of those cavities, they produce RF field. And this RF field is resonant to those resonant cavities. Now, if you change your magnetic field or your HV provided to the anode, the frequency will change. So, are you satisfied, or your question was different than that?
Thank you.
Okay. If there's no question, else, then we can take a break, 10 minutes, and then after we can continue. Thank you.